Hello all, welcome to the 8th video session of digital image processing. In the previous session, we have covered properties of 2D discrete Fourier transform, relationship between frequency and spacing intervals, translation, rotation, symmetric periodicity properties, Fourier spectrum and phase angle, 2D convolution theorem. Today, we are going to discuss filtering in the frequency domain. Today we are going to discuss additional characteristics of frequency domain filtering fundamentals, steps for filtering in the frequency domain, correspondence between filtering in the spatial and frequency domain. Then we will go for MCQ, that is multiple choice questions. Additional characteristics of frequency domain. The basics of filtering in the frequency domain. Filtering techniques in the frequency domain are based on modifying the Fourier transform to achieve a specific objective and then computing the inverse DFT to get us back to the image domain. So we can see from the figure here, it is a integrated circuit, that is a scanned image of an integrated circuit, and its Fourier spectrum of that image is given like this. Here you can see in the image, that is optical propulsion is happened. The visual analysis of an image phase angle does not give much information, but its spectrum gives the gross characteristics of an image. For example, considering a scanning electron microscope image of integrated circuit from the figure and its Fourier spectrum of that image. Here we can find the two important features, that is the strong edges are at plus or minus 45 degree and two oxide wide protrusions which are resulted from the thermally induced failure. They are at 45 degree, corresponds to the edges, strong edges at plus or minus 45 degree. Fourier spectrum of the image shows the edges are at plus or minus 45 degree. Frequency domain filtering fundamentals. Given a digital image f of x comma y of size m cross n, the basic filtering equation is given by the expression g of x comma y is equal to inverse Fourier transform of magnitude of h of mu comma v into f of mu comma v, where g of x comma y is the filtered output image, f of mu comma v is the DFT of the input image, f of the input image f of x comma y, h of mu comma v is the filter function. For simplification, use functions h of mu comma v that are centered symmetric about their center f of mu comma v multiplying f of x comma y by minus 1 to the power of x plus y. The figure, it is a result of filtering the image by setting to 0 the term f of m by 2 comma n by 2 in the Fourier transform. So the figure 8.2 is not a true representation of the image. So figure 8.3 is not a true representation of original, as all the intense negative intensities were clipped. Here you can see from the diagram that the top row is frequency domain, the bottom row is corresponding to the filtered images. It is low pass filter, high pass filter, and corresponding filtered image, that is spectrum of the filters. Here you can see the simple image A. B is resultant of blurring with a Gaussian low pass filter without padding. C is result of low pass filtering with padding. You can compare the light area of the vertical edges in B and C. Steps for filtering in the frequency domain. Given an input image f of x comma y of size m cross n, obtain padding parameters p and q. Typically, p is equal to 2m and q is equal to 2n. Form a padded image fp of x comma y of size p cross q by appending the necessary number of zeros to f of x comma y, multiply fp of x comma y by minus 1 to the power of x plus y to center its transform. Compute the DFT f of mu comma v of the image from step 3. Generate a real symmetric filter function h of mu comma v of size p comma p cross q with center at coordinates p by 2 comma q by 2. Form the product g of mu comma v is equal to h of mu comma v into f of mu comma v using array multiplication. Obtain the process image gp of x comma y is equal to real of idft of g comma mu comma v into minus 1 to the power of x plus y. Obtain the final process result g of x comma y by extracting the mn region from the top left quadrant of gp of x comma y. From the diagram, you can analyze an n cross n image. A. B is a padded image fp of size p cross q. C is a result of multiplying fp by minus 1 to the power of x plus y. D is spectrum of fp. E, the diagram E, centered Gaussian low pass filter. H of size p cross q. A of spectrum of the product HFP, G, HFG into G into GP. The product of minus 1 to the power of x plus y and the real part of IDFT of HPF. Final result G obtained by cropping the first m rows and n columns of GP. Correspondence between the filtering in the spatial and frequency domain. The distinction and links between spatial and frequency filtering is convolution theorem. If the size of the spatial and frequency filter is same, then the computation burden in the spatial domain is larger than in frequency domain. However, whenever possible, it makes more or less sense to filter in the spatial domain using small filter mass. Filtering in frequency is more intuitive. We can specify filters in the frequency, take their inverse Fourier transform, and use the resulting filter in spatial domain as a guide for constructing smaller spatial filter masks. Two reasons that filters based on Gaussian functions are of particular importance. Their shapes are easily specified. Both the forward and inverse Fourier transform of a Gaussian or real Gaussian function. Let h of mu denote a frequency domain. Gaussian filter function given by the equation h of mu is equal to a into e to the power of minus mu square by 2 sigma square, where minus the standard deviation of the Gaussian curve. The corresponding filter in the spatial domain is h of x is equal to root of 2 pi mu into a e to the power of minus 2 pi square sigma square into x square. Here you can see from the diagram the Gaussian frequency domain of low pass filter. B is Gaussian frequency domain of high pass filter. Corresponding high pass spatial filter. D is corresponding low pass spatial filter. H of mu is equal to a into e to the power of minus mu square by 2 sigma 1 square minus b into e to the power of minus mu square by 2 sigma 2 square. A is greater than or equal to b and sigma 1 is greater than or equal to sigma 2. The corresponding filter in the spatial domain is h of x is equal to square root of 2 pi mu 1 into a e to the power of minus 2 pi square sigma 1 square into x square minus root of 2 pi mu 2 into b e to the power of minus 2 pi square sigma 2 square into x square. We can note that the value of these types of filters has both negative and positive values. Once the values turn negative, they never turn positive again. Filtering in frequency domain is usually used for the guides to design the filter marks in the spatial domain. So now we will go for multiple choice questions. What is accepting or rejecting certain frequency components called as filtering, eliminating, slicing? None of them mentioned. Answer is filtering. Filtering is the process of accepting or rejecting the certain frequency components. A filter that passes low frequencies is called dash band pass filter, high pass filter, low pass filter. None of the mentioned. The answer is C. That is low pass filter. Low pass filter passes low frequencies. What is required to generate a m cross n linear spatial filter? Mn mask coefficient, m plus n coordinates, mn spatial coefficients, none of the above, none of the mentioned. The answer is A. That is generate a m cross n linear spatial filter. Mn mask coefficients must be specified. The following method is used for padding the image. Adding rows and columns of 0 or other constant gray level. Simply replicating the rows or columns, all of the mentioned, none of the mentioned. The answer is all of the mentioned. Which of the following is used as a basic function in nonlinear filter for noise reduction? Computation of variance, computation of median, all of the mentioned, none of the mentioned. The answer is B. Computation of a median gray level value in the neighborhood is the basic function of nonlinear filter for noise reduction. Convolutions are functions of distance, time, intensity, displacement. The answer is displacement. Convolution and correlations are functions of displacement. In linear spatial filtering, what is the pixel of the image under mask corresponding to the mask coefficient omega of 1 comma minus 1, assuming a 3 star 3 mask? A f of x comma minus y, b f of x plus 1 comma y, f of x comma y minus 1, x of f of x comma y minus 1, d is f of x plus 1 comma y minus 1. The answer is D, that is f of x plus 1 comma y minus 1. The pixel corresponding to mask coefficients A 3 cross 3 mask W of 0 comma 0 is f of x comma y, and so far W of 1 comma minus 1 is f of x plus 1 comma y minus 1. Which of the following is used as a basic function in the nonlinear filter for noise reduction? Computation of variance, computation of medium, all of the mentioned, none of the mentioned. The answer is computation of median. Computation of a median gray level value in the neighborhood is the basic function of nonlinear filter for noise reduction. Which of the following are a nonlinear operation? Computation of variance, computation of median, all of the mentioned, none of the mentioned. The answer is C, all of the mentioned. That is computation of variance and computation of median. Computation of variance as well as median comes under nonlinear operation. In a neighborhood operation for a spatial filtering using a square mask of n star n, which of the following approach is used to obtain perfectly filtered result irrespective of the size? By padding the image, by filtering all the pixels only with the mask section that is fully contained in the image, by ensuring that center of the mask must be at a distance greater than or equal to n minus 1 by 2 pixels from border of the image, none of the mentioned. The answer is C, by ensuring that center of the mask must be at a distance greater than or equal to n minus 1 by 2 pixels from border of the image. By ensuring the center of the mask must be at a distance greater than or equal to n minus 1 by 2 pixels from a border of image, the resultant image would be of smaller size, but all the pixels would be the result of the filter processing, and so is a fully filtered result. In the other approach, like padding effect, the values near the edges that gets more prevalent with mask size increase, while the another approach results in the band of pixels near border that gets processed with partial filter mask, so not a fully filtered case. So we will end the MCQ here and we will end the session also. Thank you very much.